So we have our last unit test coming up on Monday on simple harmonic motion and waves. Here's the simple harmonic motion part of the unit. We started off with Hooke's law, although we did that primarily in our dynamics unit way back in unit 2. We revisited it in this unit. The reason we did is because Hooke's law is effectively the definition of simple harmonic motion, right? The idea that F is equal to K times X. The idea that motion that repeats itself is motion that has the restoring force proportional to the displacement. Bigger the displacement, bigger the restoring force. It's Hooke's law. Okay, so be familiar with how to use Hooke's law. Also be familiar with elastic and spring potential energy, which we also did back in our dynamics unit, in our unit 2 forces unit, but revisited here with our simple harmonic motion unit. You guys know that the elastic or spring potential energy is equal to 1/2 kx squared. Know that sometimes we have to find the value of k using Hooke's law to plug into here. Sometimes we have to find the value of k using this equation to plug into Hooke's law. We talked about the pendulum, the things that affect the period of the pendulum. It's the length of the pendulum, of course, the gravitational field strength or acceleration due to gravity. And then, of course, we talked about resonance, resonant frequency, and resonance. The idea that when we apply a force at a certain frequency, at the resonant frequency or the natural frequency of the object, then it's going to cause the vibration to grow, and sometimes to grow to the point of failure in that object, the object breaking, like the glass with the opera singer or the bridge with the wind. Let's spend a couple minutes here, guys, while we're on this page, just rearranging these equations, okay? Because there's a couple equations here that are a little bit of a challenge. Okay, first one, not so bad, right? We want to solve for k, that's pretty easy. If we want to solve for x, that's pretty easy as well. Okay, no rocket science on that one, I don't think. This one's a little bit tougher. We want to solve for k here. Now we're going to say, what are we going to do? Take over the half and the x squared. It's going to become EP over 1/2 x squared. It could also be 2EP over x squared, right? We could take over that 1/2 by multiplying by 2, either one. X is the tougher one to rearrange for, though. We're going to say EP, x is equal to, what are we going to say? EP divided by 1/2 k, or you could say 2EP over k, either one of those. But we got to get rid of the square as well. We're going to do that by square rooting. So x is equal to the square root of EP over 1/2 k, or the square root of 2EP over 1/2 k. Now the last one, this is the one that we really had a tough time rearranging, although I think you guys got pretty good at it by the end. Solving for L, we've got to get rid of the 2 pi first. So it's going to become T over 2 pi is equal to the square root L over G. Now we got to square it. So it becomes L over G is equal to T over 2 pi squared. Then we got to get rid of the G. So solving for L, it's going to be equal to L is going to be equal to G times T over 2 pi squared. If you're solving for G, well, you're going to do the same thing as we just did, except you're going to go one step further and divide everything by T over 2 pi squared. So it becomes G is equal to L over T over 2 pi squared. And you can simplify that, right? Okay, you could simplify that a little bit. There's an equation in our book that some of us saw that we used that was a little bit of a simplification on this, but in the end it was the same thing. So we'll go with not the easiest equation to write, but the easiest equation to rearrange. That's what we'll go with. All right, then we move forward to waves after just a few days of simple harmonic motion. And we talked about the relationship between simple harmonic motion and waves. The idea that wave motion really is just the simple harmonic motion of individual particles. Waves carry energy, right? How do they carry energy? Because there's simple harmonic motion of individual particles within those waves. We talked about the 2 kinds of waves, transverse versus longitudinal. We know that longitudinal waves are the ones that have to be in a gas. Okay, we can have longitudinal and transverse in a solid, but if you've got a gas, you can't have a transverse wave. It's got to be a longitudinal wave. We talked about the direction of motion of the particles in both kinds of waves. Okay, if the wave is going to the right in both cases, cases, the particles are vibrating within simple harmonic motion perpendicular to the way the wave moves if it's transverse, and parallel to the way the wave moves if it's longitudinal. We defined a couple of terms on these. The wavelength. The wavelength is the distance over which the wave repeats itself. A crest is the bump on a wave. A trough is the dip on a wave. A compression is where the wave, longitudinal wave, is compressed, and a rarefaction is where it's stretched. The amplitude of the wave is measured from the equilibrium position to the top of a crest, or from the equilibrium position to the bottom of a trough. We talked about the speed of waves, and of course, the speed of waves, ultimately, unless it enters a new medium, as long as it stays in the same material, the speed of the wave isn't going to change. Therefore, we can describe it by the equation V equals d over t, but we can also use the equation V is equal to F times lambda, which really is just d over t, but a specialized form of it. We derived V is equal to F times lambda to show you where it came from. In the end, you don't need to derive it. It's on your data sheet. You just need to be able to use it. A couple other equations that maybe might go with that. Okay, for frequency, we say 1 over the period. Okay, maybe frequency is the number of cycles divided by the time, or period, you could say, is the time divided by the number of cycles. What do we mean by this wave behavior at boundaries? Well, when a wave encounters a boundary, two things can happen, right? In fact, two things will happen. You always get some of both. First one was reflection, and the second one is transmission. If the two materials are real similar, you're going to get mostly transmission. If they're real different, you're going to get mostly reflection. When it reflects, it can reflect right side up or upside down, depending upon what it hits. If it's attached to the new medium, it's going to be reflected upside down. If it's going from less dense to more dense, it's going to be reflected upside down. If it's not attached, if it's a free end, it's going to be reflected inverted, right side up. Or if it's going to something that's less dense, it's going to be reflected right side up. Transmission. Well, when the wave goes into a new medium, something stays the same. What is it that stays the same? Always, once a wave has been made. The frequency stays the same. What changes? We know the speed changes, right? Think of that soldier analogy. The speed of the wave changes. What will change in response to the speed changing because the speed changes? What's one other thing? The direction. So we'll say theta there will also change. The wavelength will also change. Again, think of that soldier analogy. What changes? The direction changes. The wavelength changes. Interference in the superposition principle, that's just basically when one wave hits another wave and we get a new wave form, sometimes constructive interference, sometimes destructive interference. You got a wave right here. You got another wave right here. Okay, what does the resulting waveform look like? Well, it's going to be something like that, right? You have to figure out exactly what it looks like, not something like that. But of course, to do that, you're going to just count the number of blocks. It'll be given to you on graph paper if you get one of these. Okay, you're going to count the number of blocks each of those waves is above or below, add them up, and then draw your little red X's where the sum of those waves is. Call it the superposition principle. We talked about diffraction and interference. Diffraction, the spreading out of a wave. Remember that the amount of diffraction is dependent upon three things. The size of the opening. Size of the opening increases. What happens to the amount of diffraction? Decreases, right? Smaller the opening, more diffraction. If the frequency increases, what happens? Frequency of the wave, that is, increases. What happens? Small frequency gives me AM radio, remember? AM radio, small frequency gives me more diffraction. Okay, and of course, FM radio or big frequency would give me less diffraction. What about wavelength? Well, it's exactly the opposite of frequency, right? So if small frequency gives me more diffraction, then small wavelength will give me less diffraction. And we talked about diffraction and interference when we had two openings. So it's not just the one opening with diffraction taking place. It's, and here's a situation where you have two openings. And the waves are coming upon this, and they hit the opening, and they spread out and diffract like this, but they kind of get in the way of each other. Well, when we have a crest and a crest meet, we get constructive interference. When we have a crest and a trough meet, we get destructive interference. And when we get a trough and a trough, it's constructive again. So ultimately what we end up getting is these alternating lines of constructive interference and destructive interference. So you're lying on that air mattress in the swimming pool where you have this double slit experiment taking place, where you have this diffraction from two openings. You're lying on one of the red lines, constructive interference. You're going to be bobbing up and down like crazy because it's big waves, really big waves, because it's constructive interference. But if you're lying on one of those green lines where it's destructive interference, then what's going to happen? Nothing. You're just going to relax there because you're not bobbing up and down at all. The person next to you is bobbing up and down like crazy. You're just relaxing on the air mattress there. Standing waves. Running out of space here. Standing waves, remember we had three types of situations. We had the first situation where we had a string that was attached at both ends. The second situation was when we had an air column that was, we call it a closed air column, that was open at one end, closed at the other. The third situation was where we had an air column that was open at both ends. Remember to draw the pictures here. When it's a closed end or a fixed end, you have to have a node. When it's an open end, you have to have an antinode. So in the first one, you get two nodes. In the third one, you get two antinodes. In the second one, you get a node and an antinode. All right, so three different situations here. Okay, in all three cases, we can define a length in terms of wavelength. This is a half of a wave. This is a quarter of a wave. And this is, once again, a half of a wave. Lambda is therefore equal to 2L. Lambda is equal to 4L. Lambda is equal to 2L. F is equal to V over lambda, or F is equal to V over 2L. F is equal to V over 4L, V over lambda, or V over 4L. F is equal to V over 2L. So, first harmonic, second harmonic, third harmonic? No. First harmonic, and first harmonic for three different things, right? What would the next harmonic be for this one? Just give me a relative value. Okay, compare it to this one. Yeah. V over L, or you could just say it's twice the first one. Yeah. Okay, it's twice the first one. We call that the second harmonic. The next one is 3 times the first one. The third harmonic, 4 times. The fourth harmonic, and so on. Okay, first, second, third, etc. Same deal with the bottom one. This is the first harmonic, but we can also have a second harmonic and a third harmonic, etc. But the next one, the middle one, we have a first harmonic. We have 3 times the first harmonic and 5 times the first harmonic, but not 2 and 4. In other words, we have the first, we have the third, we have the fifth harmonic, etc., but no even number harmonics. You can't physically derive an equation that's twice the first harmonic there for that middle diagram. And finally, the last thing that we have here is the Doppler effect, and that's what we learned yesterday. Remember, as it's coming towards us, higher pitch, as it's going away from us, lower pitch, the equation FD VW over VW plus or minus VS. over Fs. This is the thing that I want to draw attention to. Make sure you know the variables, right? Make sure that you know, remember that Vw is the speed of the wave, not the speed of something else. Vs is the speed of the source, not the speed of sound. Okay, but the big thing here is this plus and the minus. When the source is coming toward me, what do I make it, plus or minus? Oh, you remember that, eh? Some people are going to remember. That's fine. I'm not asking you to remember. I'm asking you, if you don't remember, just to figure it out, right? Okay, if it's coming towards us, we know that FD has to be a bigger number. And if FD is going to be a bigger number, then VW minus plus or minus VS, the number on the bottom here, has to be a smaller number. You want big here, you want small here. And you get small here, you're going to subtract them. So if it's coming towards me, then I'm going to subtract. And if it's going away from me, okay, well then I want to have a smaller number for FD, and if I want to have a smaller number here, I want to have a bigger number here, and a bigger number here is going to come from adding them together. Yep.
You don't want to search for it, but I remember it because the way it adds.
Okay. You know what? No, honestly, I'm okay with you remembering it. If you have a way to remember it, that's not going to be one of those things where I remember it for the next 4 hours and then forget it again, right? If you can remember that long term by saying away, add, okay, that's fine. Okay, that's not a bad way, actually. Okay, I never actually thought of that way before, but that's probably quicker than the way that I did it. Okay, if you think of away, it's going away from me. Okay, add them together. They both start with the letter A. Okay, that works for you guys, and that's great. So we had a request to go over one of those one of those interference problems, guys, where we have crest, trough, whatever. We want to find out whether it's constructive, destructive, exactly what the resulting interference pattern looks like. This is the one that was on your practice test that I uploaded to Google Classroom here maybe a week ago. I don't know if you've had a chance to do this or not. I know that some of you have. If you have, great. If you haven't, just follow along anyways, but try it yourself when you go home just to make sure that you can do it yourself. All right, first part of it's easy. Okay, we don't need to worry about interference rate here, or 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 here, because there's nothing overlapping here. Same deal over here. Well, basically here. No, there is overlapping right to the end there, okay? So it's only at one end where there's no overlapping taking place. So at this point, we know what the resulting waveform looks like. Everywhere else, we got to figure it out. All right, so let's do that now. Let's look at this line right here. We got 1 above. We got 1, 2, 3, 4, about 4.5 below. 1 plus negative 4.5 gives me negative 3.5. And you don't have to be perfect with these. Okay, they don't have to be absolutely perfect. If it's 3.4 instead of 3.5, oh well, right? If it should be 2.5 and you put 3.5, well, that's wrong. Okay, if it should be 3.5 and you put 3.25, that's okay. I can live with that, okay? We're not measuring with a ruler here to get the exact values. You just want to be relatively close. Okay, about 2 above, about 4 below. 2 plus negative 4 gives me negative 2. 2.5 above, 3 below. Okay, that's about negative 0.5. Okay, 3 above, 1 below, about. Okay, it's going to take me to about right there. What do we got here? 0 and 3 above. 2 above and 3 above gives me 1, 2, 3, 4, 5 above. 3 above and 3 above gives me 6 above. 3 and 4 gives me, oops, ran out of space, 7 above. Making sense, guys? Is that making sense? What do we got here now? 2.5 and 1, 2, 3, 4, 4.5. 2.5, 4.5 gives me, is that 7? 1, 2, 3, 4, 5, 6, both the same place. 2 and 5. 2, 3, 4, 5 gives me about 7 again. 1 and 5 gives me about 6. And then we're down to here. Okay, because it's 0 and 5-ish. 1, 2, 3, 4, 4.5 above, 1.5 below, gives me about 3 above. 4 and neg 2 gives me 2. 3 and neg 2.5 1.5 and -3. So it's going to look something like this, right? All right, so what do we have, constructive or is it destructive interference? Well, it depends on where you're looking. Let's look at this spot right here. Constructive or destructive interference? We call that destructive interference, right? Because we're making something that's smaller. We're adding a crest and a trough together. We're making something in between the crest and the trough. What about this area right here? That would be constructive interference because you got two crests together, right? Constructive interference. And what about this section right here? This would be destructive interference because you've got a crest and a trough coming together, right? Now, that's not going to happen all the time. Sometimes some diagrams you see, simpler diagrams, are going to have constructive interference all the way across. Okay, some of them might have destructive interference all the way across. Constructive, destructive, whatever. This one happens to have some constructive, some destructive, depending upon where you're looking. Okay, okay, fair enough. Okay, so it's generally it's probably going to be a problem where you have just constructive or just destructive. In this case, it just happens to be some of both.